So I'd like to continue so yesterday we talked about I talked about the prompt emission models. So I'd like to basically the classical model for the prompt emission is a synchrotron internal shock synchrotron scenario, in which the particles are accelerated at internal shock, which can be caused due to the inhomogeneity inside the jet, and then the electrons emit a synchronous emission, which can be in the MeV range. And then alternatively, then people discuss the magnetic dispersion scenario in which the particles, electrons are accelerated by reconnections or turbulence. Then again, the synchronous emission might be responsible for the MeV emissions. But one of the, there are three possible scenarios which have been discussed actively in the literature. Then actually, these three possibilities are not exclusive to each other. But anyway, one of the, one of the three scenarios is a photospheric scenario in which the gamma ray emission, the MeV emission, is attributed to the quasi-summer or summer emissions. So at least we know that for the sum of gamma ray bursts, such as summer emissions exist. So as I showed yesterday, and some of the GRBs which are detected by Fermi satellite show a very hard spectrum. This is an energy spectrum, nu F nu. Then again, the spectrum can be described by the smooth broken power, so-called band function. But you see that the spectrum index is very hard. So basically, the rising with 2.3, then black body is 3. So a bit different from the black body, kind of in the sense modified. But it's not synchrotron. In the synchrotron, the hardest spectrum is 4/3. So you cannot explain this component by synchrotron emission. And then even in the, some people think that, it's more, such a bump may exist in the sum of gamma ray burst. So this is a kind of regarded as evidence for the summer component, and which is actually quite natural according to the fireball model. Because in the fireball model, initially you expect that jet has a lot of radiation, right? Then eventually the radiations, radiation energy is converted to kinetic energy. But when at some point, initially the photons cannot get out because the system is optically thick. Because of a lot of scatterings, photons cannot get out. But at some point, density is lower. In this case, photon can get out. And at this point, the photons, some photons are expected to be summer. So this is a kind of photospheric scenario. So essentially, initially, you can define the Thomson optical depth is this is basically the optical depth, but due to the Compton scattering, and this is the estimate is this, and the number density of the electrons, and then cross section, Thomson cross section, and the size. Then I just put a prime because as we talked yesterday, you have to think about the frames. So the number density is defined in the plasma frame, which is comoving and in the frame of the jet. And then this L prime is a comoving size, basically the size measured in the rest frame of the jet. So if you remember what we discussed yesterday, so the L prime is order of the R over gamma. So I think that if you don't remember, then I think that, so a bit far. Here. So this one. Actually, we discussed this part. So the comoving size is basically the R prime is CT prime, kind of, right? it's a C delta T prime. And then this is over C2 gamma delta T. So basically, the people do not care about the 2s. Then some people put 2, and some other people do not put 2. So usually it's a kind of order unity factor, which should be regarded as uncertainty. So this is L is essentially orbital gamma, and basically this is kind of the people use this function. This is R, and over gamma, and this is cross section. Then of course initially this number density is huge, and prime is huge. Then system is optically thick. Then basically the photons scatter a lot, so experience many scatterings. Then eventually, even if the photons are generated non-summary, then what you expect is a summary spectrum. The eventually system becomes optically thin because the flow jet is expanding, right? And then tau decreases, and then when this tau t becomes unity, right? And then you can actually, at this point, you can define the photospheric radius. This gives the photospheric radius, then R photospheric. Then actually, one of the questions, exercise problem, is actually to calculate photospheric radius. Okay, so then you can calculate it. Okay, so then when the optical depth becomes comparable to unity, around the photospheric radius, eventually in the beginning the radiation is trapped. At this point, the photons start to get out, right? And then if you don't have any non-dissipations, you expect summary emissions. But if something's going on, for example, the jet keep interacting with stellar material or ambient material, in this case, still you have some energy dissipation. In this case, in principle, you can expect some modification. Or also it's a relativistic effect because of radiative transfer problem, and there's some modification is expected. Anyway, this is the kind of essentially the photospheric scenarios using this summary component. You can try to explain this kind of MEB emissions, and this works. And for example, the heating mechanism is actually in the debate. But for example, because around the photosphere, the density is so high, and then actually just even if you don't have any weird dissipation process, in principle you can have a Coulomb heating, and the Coulomb heating can the heat can give the energy to the electrons, and this kind of Coulomb heating that can allow us to explain the two components, basically double power spectrum. Or if you put the magnetic fields in addition to the Coulomb heating, then it's quite natural because the jet is also expected to be magnetized. It's kind of because it's very difficult to imagine that jet has zero magnetic field. So because central ranging is actually the magnetized because whatever you have, right? Black hole with accretion disk, and accretion disk has magnetic fields, and the magnetars also have magnetic fields. So then basically the jet should carry some magnetic fields. And then you expect the magnetic fields, and then some synchrotron emission is expected. And then yes, and then once you put some synchrotron emissions, then you can actually have a kind of modified summary spectrum, which is consistent with observation of the prompt emission. So then, yes, the kind of the people now are calculating this problem in the more quantitatively, because this problem is actually in principle the summary emission, right? This is summary emission. So you can actually calculate you can actually rely on the simulations. So because for given star, right? You can bring some star, progenitor star, such as Fly star, and you can put the jet. And the jet can propagate. You can simulate the propagation of the jet, and then you can calculate how the radiation transfer happens, and then eventually you can calculate how the emergent emission looks like, right? And this is possible, doable, right? And people do this kind of calculation recently. And this is a kind of the one-dimensional simulations. Then right here, this is a kind of 3D simulations. People inject jet. And then basically you see that jet is actually, this is a Lorentz Factor distribution. And then you see that in a jet here. And then at the time, basically you see that after the jet breakout, and the jet is actually there, and but some material is around. Because of the interaction between the jet and the stern, you have some material, kind of heated material. And then people indeed show that because of simulations, it's possible to achieve the peak energies around MeV energies, and which is consistent observation. And then this kind of photospheric emission scenario is appealing, then because I introduced a relationship between the peak energy and the luminosity. And this is data. But this scenario, because this is summer emission, right? This photospheric is summer emissions. So in a sense, actually, you expect that some relationship between the luminosity and the temperature. And the temperature is related to peak energy because of summer emission, right? Temperature is essentially this peak energy is determined by the temperature, okay? And then the temperature and the luminosity is related, right? And according to the black body radiation, basically the luminosities, the R squared, the T to the 4, proportional to the R squared and the T to the 4, right? In the summer black body limit. So if you think about based on the analogy of the black body radiations, you expect that there's a relationship between luminosity and the peak energies, and then indeed our simulations suggest that it's possible to explain the relationship, spectral relationship, in this scenario. And then I think this is the one thing which we don't know, because the MeV band, it can be explained by the photospheric emissions, but the Fermi satellites see the gamma rays in the GB band. This part is clearly non-summer. So you need to invoke something. And then this part is, we don't know. So basically you need some dissipation. So the particles indeed accelerated. And then people discuss two possibilities. One possibility is that the electrons accelerated, and the impulse upscatters these summer photons, and you have inverse Kohta emission. This is the most popular interpretation. But in principle, you can think about other possibilities, hadronic scenario. And in this case, the protons accelerated to very high energies, and these protons actually accelerated, and they interact with photons, and you have pions, and the pion decay, and you have gamma rays, and electron positrons. But in this case, the story is complicated, but very high energy gamma rays cannot get out because system is a lot of radiation there. Then eventually the gamma rays interact with low energy photons and the pairs. And these pairs, again, emit the synchronous emission, the inverse Kohta emission. And if inverse Kohta emission is still high energies, and still, again, these gamma rays interact with the low energy photons again, this process repeats. This is so-called electromagnetic cascade. And then in the hadronic case, you have to think about these. But in principle, this kind of hadronic cascade model can explain this kind of high energy band. But at this point, we don't know. To prove this model, or to test this model, probably we need the data at the very high energy gamma rays, and which maybe happen in the future because Cherenkov telescopes now detected the gamma rays in the 1 GB range. Well, neutrino experiments may tell us about the mechanism. And then one thing which is related to exercise, and this is actually related to the Lorentz factor, because I said that GRB jet require the highly relativistic Lorentz factor, large Lorentz factor. The reason why I said that, initially, I think in the introduction yesterday, I introduced a compactness problem. What is the difficulty in the X-ray scenario? And then if you put a lot of energy in the small region, you have a problem because gamma rays cannot get out directly, and you have high energy gamma rays with interactive low energy photons, and you have pair creation process, right? Two photons annihilate, and the electron positons are produced. And then if you consider the system is not moving, this process is unavoidable. There are a lot of interaction happen, then this is a compactness problem. You never get a non-summary spectrum. And then the how you save this problem is actually the Lorentz factor. So if you put the Lorentz factor, which is larger than unity, much larger than unity, you assume the jet, actually you can reduce the optical depth a lot. Basically, if you calculate this tau gamma gamma to the gamma gamma this pair correspondence process, and then this factor, this optical depth is a strong function of the Lorentz factor. Okay, and then using this fact, basically you can actually make an estimate on the Lorentz factor, because I think this is depends on the Lorentz factor. And then this is actually one of the problem in the exercise, actually. And then this is a Lorentz factor. Basically, if the Lorentz factor is large, then optical depth is lower. And then basically, the fact that you detected very, very high energy gamma rays enables you to put a lower limits on the Lorentz factor, right? Because higher energy photons are more difficult to escape, okay? And then let's say that you have 100 GeV photons escape, 30 GeV photons escape, and then yes. So the fact that you see, okay, here you see these photons, right? And basically this means that the optical depth for the 30 GeV must be less than unity, because we don't see any absorption feature in the spectrum. By requiring these conditions, and then you can basically limits or put the limits on the Lorentz factor. Is okay? So this is basically the tau gamma gamma is a very strong function of the some index. Basically, I would say probably I put some alpha or something like that. Alpha is confusing because this depends on the spectral index, actually. So using these, and then you can put the limits on the Lorentz factor, and then if you calculate this, actually, in the case of Fermi GRBs, Lorentz factor, lower limit of Lorentz factor is around close to 1,000. So this infers that Fermi GRBs might have a Lorentz factor which is quite large. Okay, super hard realistic. Okay, so now you can discuss the afterglow model. So I think after the internal shock happens, then eventually the jets start to interact with the external medium. And then still we have a relativist shock, and the particles accelerated, and the electrons emit synchronous emissions. So there are three ingredients for this kind of the calculation. The first, you need to know the dynamics, because once the jet interacts with the external medium, you have a shock. But eventually, the shock starts to get decelerated. This is described by the Brandford-Markey solution. The second ingredient that you have to assume that the electrons are accelerated. And then usually, the people just assume the simple power law. Or in principle, you can consider the more complicated stuff. And then the third ingredient that you can calculate the synchrotron emissions and plus inverse Compton. So what is how you can calculate dynamics? So basically, this is a dynamics described this kind of the Brown-Holomack solution, Brust-Wave solution. Let's consider just initial explosion. Then basically that puts the explosion energy E, okay? Explosion. Oh, oops. Yes. And then, I don't know why this happens frequently. So this is a relativistic case. So the energy of the ejector is written as a gamma 0 m0 c square, okay? It's a kind of, gamma 0 is just initial Lorentz factor. The m0 is just baryonic mass. And eventually, because after explosion happens, basically we have shock, and basically the external material is swept up by this shock, okay? And it becomes the layer, the shell in the shock direction. The shell becomes heavier and heavier because this mass is entwined in and shocked, and this part becomes heavier and heavier. So when this relation happens, is that basically when the baryonic mass is swept up mass is comparable to the m0 over gamma 0 because of relative scale effect. So this means that m0 is E gamma 0 square, and gamma 0. And the M is just, how much the shock sweeps up the volume, right? Basically, this is volume, right? If you consider this kind of here, size, this is size, this is basically the initially initially here this point, right? But the material which exists in this volume is swept up by the shock, and basically then concentrated is a very thin shell here, this region. And this is mass. This mass is here. This is M, and this 4 pi over 3, and then MPN R cubic. Is okay? So then you can relate E is pi and then gamma 0 square and then MP gamma 0 square, then N MPC square and R cubic. So later, this when this is satisfied, this relation starts. Okay, this relation starts, and then basically this gives the deceleration radius. Deceleration radius. And then 4 pi R3 and then gamma 0 square. Is something like that. Okay? Then basically at this point, the ejector, so the jet start to get decelerated. Then after the deceleration radius, and basically the energy, if you consider the, eventually some energy is radiated. But as long as this, the radiation loss is relatively small compared to the total energy, basically you can apply the adiabatic approximation. Basically, in this case, energy is conserved. Okay. So that this implies that after that is constant, and then this is still energy of the ejector is something like this: gamma square and pc square r cubic. Is okay? Then in this case, gamma is now the function r, because after the jet deceleration radius, then basically the jet, the flow starts to decelerate, burst wave starts to decelerate. Lorentz factor decreases as time. Okay. So in this sense, because in this case you can find that gamma square is proportional to the r to the minus cubic, and this is that gamma is.
It's not true in this.
Whoa. Okay. What? Yes, something like this. So this is happens when the r is larger than deceleration radius. Okay. Is it clear? One more thing. You probably observer, if you are observer, so that you need to know, you want to know the evolution as a function of time. Okay? As a function of time, which is measured as the observed time, right? Then now again, you need to remember what we learned yesterday. So what is the relationship between the r and t? So, okay, so the question is that, do you remember that relationship dt hat? If you, and dt, what is the relationship? I think that you need to put some Lorentz factor here. Do you remember? Sorry? Yeah, Doppler factor, but question is that gamma or gamma square, or because this is dimensional factor, you need to think. I think that we discussed the propagation effect yesterday, right? And actually, you saw that relationship between the dt hat and dt. This is the observer, and this is the engine frame. Do you remember? Why?
Gamma times 1 minus theta.
Right. Yes, dt hat this kind of, okay, so if you don't remember that, I can go back again. I don't know the good way to go back. Okay, this here. Oh. Why does this happen? It's completely lost.
No, it's right.
Oh, okay. Hi. Yes, this part. So here, dt, this is the observation time difference, is approximately dt hat over 2 gamma square, right? So basically this part. Then you remember that, okay, if you consider R is how you express R, the emission radius. R is actually CT. R is CT because of relativistic, but this T is what? T, which T? T hat, yes, because this is engine frame, right? So that because the explosion happens, right? This CT, right? Explosion happens, then if you measure as a function of the time in the engine frame, and then basically the speed of the, speed is relativistic, they almost C. Then basically the radius is just CT hat. And T0 is basically the kind of explosion time, the onset of the explosion. So this means that if you consider this CT, if you want to write down that this as a function of the observational time, you get this. Okay, so this R is proportional to the kind of order of gamma square CT is a kind of the, relationship you always see in the context of gamma ray burst. Because you always need to convert, okay, so what is the emission radius? But what you know, we have the information as observation time T, right? Then if you want to estimate, you need to know the R and the L prime, whatever. In this case, if you want to calculate the R, basically the order of gamma square CT, special relativity effect. And then, yes. Then detailed factor of the, I don't explain the detailed factor of the two or which factor should be put. But roughly speaking, as I said, this is a gamma square. Then R is 2 gamma square CT, okay? Okay? And then in this case, I should put the R, large R. And then if you put this, actually you can calculate deceleration time. Okay, so this means that at this deceleration time, still the ejector has not started the deceleration seriously. So basically what it means that deceleration time is R deceleration and 2 gamma 0 square. Is okay? And basically you put the gamma 4 pi gamma 0.8 NPC square and 3E and do something like that. Is a question?
No, nothing. It's just natural units.
Okay. Oh, natural. Yeah. Is okay? So that this is actually gives a deceleration radius, okay? And then you can actually translate this relationship and then as a function of t. So what you get? Because again, gamma is r to the minus 3 over 2. Then r is actually the proportion to the gamma square t, right? And then basically the gamma minus cubic, and then t minus 3 over 2. Then this means that gamma 4 is proportional t to the minus 3 over 2. You okay? Just scaling. So the final result you should get is that gamma is proportional to t to the 3 over 8. And then after the t is after the deceleration time. Okay? So that you get the picture? So basically until the deceleration time, probably the jet is kind of the burst wave is constant with some Lorentz factor, gamma 0. Then when this burst wave is actually sweeps up the sufficient amount of the material, external material in the shell, and then of course you start to feel the deceleration, and this happens at the deceleration time, t deceleration, and the Lorentz factor decreases as a function of t, and then this is a proportional to the inverse of the 3/8. Okay? So this describes the dynamics in the Brandon-Hodel-Markey phase. So you can actually give the solutions, self-similar solutions, and then this was first derived by Brandon-Hodel-Markey in the late 70s, the middle of 70s. So now you need to calculate. So the synchrotron emissions. So yes, so we don't, in the calculations, people usually assume that, for simplicity, assume that electron spectrum is polar. And then, okay, if you have a good descriptions, then you can put your acceleration spectrum. But for precision, the people just assume the synchrotron electron spectrum with a polar. And then basically, people consider this kind of spectrum. So okay, again, I put a prime explicitly because I define the spectrum electrons in the comoving frame of jet. Okay, because still even if even in this case, still you have a Lorentz factor which is larger than 1. And then you have a polar spectrum, D and EE. This is the electron spectrum. And then you can define the minimum Lorentz factor. This is the gamma m prime. And then you can think of the power law. So it's gamma E prime minus S. Okay, this is an assumption people usually take. This is an injection spectrum. Then you have to determine the normalization, how many electrons are accelerated, right? And then people usually consider that, okay, number of electrons, if you consider basically if you consider the electron, people usually expect that the ambient material is a proton-electron plasma. In this case, the number density of the electrons is the same as the number density of protons. And then if you assume that all the electrons are accelerated, and then you have put NE. So that if you consider only a fraction of the electrons accelerated, then people usually put the FE. This is the number fraction. And then you can put this factor or not. Then this depends on the people. And then you can calculate the minimum Lorentz factor. This is always order of these. So actually, in order to explain this, actually, you have to think about shock physics. Actually, not this. Sorry. Okay, good. So in the case of the blast wave, so you have a shock, right? And then this is the external media. Then this is regarded as upstream. And then initially you have a density, okay, N. And let's consider cold material. So basically, let's ignore the temperature in the upstream. And then in this case, you can calculate the density of the downstream because this is a shocked region here. This is shocked. Okay. Basically, in the left frame of the engine frame, this is the ambient, and the shock is coming with some Lorentz factor. And then here, basically, I show this picture in the left frame shock. Basically, I did some Lorentz transformation. In the left frame of the shock, basically, the upstream material is coming, and the downstream material is outgoing. Okay. And then you need to relate the relation, the downstream density and upstream density. And you also need to know the energy density of the downstream. Okay? This is the energy density. Then, unfortunately, probably I don't have time to derive all the Rankine-Hugoniot relationship in the relativist case. I just describe the results. So in the limit where the Lorentz factor is much, much larger than unity, basically the n prime is described by this. Just shock the compression, right? Lorentz factor is gamma, then compressed. The density is higher by factor of gamma. So it's a cold material. And in this sense, you should expect that the NMPC square, because you consider cold electron ion plasma. Then basically, most of the energy is actually less mass of the protons. Okay? And then in this case, density is enhanced by gamma. But because of the shock, and the energy per particle is also boosted by gamma. Okay? And then you have another gamma. Then I just described the result. And then this is a kind of the relationship and expected for the relativist shock. So this is actually the energy density in the downstream. Basically inside the shell. And this is the number density in the downstream. Okay. Then in the so you have the important thing that you have a gamma square and gamma. Okay. Then basically magnetic fields, basically people assume that this is a downstream energy density actually. This is the E prime, kind of in a downstream energy density. And then people just introduce the phenological parameter is so-called epsilon B. The fraction of the energy density is converted to the magnetic fields. Okay, phenological prescription, they just assume this. And then, this is a magnetic fields is this factor. And then you expect that B square is proportional to the epsilon B and the gamma square and the N. And then if you think that N is constant, epsilon B is constant, then basically you expect that gamma is proportional to the T to the 3/8, and you get the T to the minus 3/4. This is scaling. Yes. Does it make sense? So magnetic fields actually you can estimate magnetic fields based on these dynamics. And the Lorentz factor you can determine. So again, in this case, assumption is that here. So basically, here I think it's better to calculate. And so same thing, because I said that electrons, you assume that, you assume that this spectrum, this is the electron spectrum. So total number of the accelerated electrons is NE, and then basically this is determined if you consider that maximum energy is very large. Let's ignore, and in reality you have to take into account, but let's ignore. And then in this case, this gives a total number of accelerated electrons, right? Right? Is okay? Just integration. Then here, I assume that this is power law, gamma A, it's the minus S. And you have the minimum Lorentz factor. Is okay? And then if you do these integrations, you get the gamma one, so S minus 1, right? And then, as I said, this is a 3, 4 pi n p mc square, and then r, sorry, n, sorry, I was wrong. The cubic, okay? Right? This is volume and number density. Is okay? And then the also important thing is that this is also related to the sorry, actually here is a bit confusing. Anyway, let's keep going. So you can also calculate the energy fraction of the electrons. Then basically how many electrons just what is the energy carried by electrons? Okay, this is actually the given by here. This is a large coming to the calligraphic E, and this is given by this. And you have to calculate the gamma E MEC square, and then this is the electron energy, and this. Is it okay? And if you do these calculations, then basically you get the MEC square, and then gamma A, and then gamma E, sorry, S minus 2, because you have this is a proportion to the gamma E to the minus S. Then you have S minus 2, and the gamma E to the S minus 2. Something like that. Okay, now you have to think about one thing. So actually this is related to this calculation. So here, basically people consider phenomenologically this is a kind of the proportional to in the downstream frame. So sorry. This energy, total energy of the electrons, is actually comes from the energy density in the downstream. So we assume that energy fraction of some energy fraction of the downstream energy is converted to the accelerated electrons. This is a phenomenological prescription, which is similar to what I assumed for the magnetic fields. Okay. So in a sense, people usually consider this is epsilon E. And then you have a gamma square, and then some volume. And this is a volume of the shell. And then this NE is in the same split. If you consider this, basically you have gamma N and the volume in the shell. Okay? Volume of the shell. So to avoid the confusions, let's actually both are actually consistent, but it's to avoid the confusion. So let's remove this actually to avoid the confusion. So basically proportional to the gamma n and the prime, and then this is a gamma square epsilon E in the n p prime. Okay, does that make sense? So you have two relationships, and you can divide this stuff, right? So because S minus 2, S minus 1, and then actually you can actually estimate one thing. In order to have the unit, I need to have an MPC square. Sorry, because I should keep the dimension. Okay, sorry. And this. Okay, good. So using these two relationships, and then basically you can calculate. So MEC square
then S minus 2, and then S minus 1, and the gamma E prime. Sorry, so the gamma minimum, sorry. It's gamma minimum. Gamma minimum. And then you have a gamma, and then this n is V is cancelled out, and then you can ignore. The C squared is cancelled out. And then basically you have gamma, epsilon E, and P squared.
Is it okay? Is it okay?
So C squared is cancelled out. Oh. So the finally, you get that M gamma M prime is S minus 1, S minus 2, and epsilon E, and MP over ME times gamma.
So then basically, if you assume the spectral index S, and then gamma can be determined by the dynamics, right? The dynamics, Brondel self-similar solution. And then if you give the epsilon E, then basically you can estimate, you can give the minimum Lorentz factor. Is okay? So then this kind of, roughly speaking, the epsilon is proportional to epsilon E, the MEB over ME, and the Lorentz factor. Then this is, again, the gamma is proportional to the T to the minus 3 over 8. You can calculate. And then cooling Lorentz factor, so that you can calculate the corresponding synchrotron frequency. Synchrotron energy. So the synchrotron frequency is Vm, nu m, right? This is the frequency. Okay. Then if you consider this, 2 pi gamma m square and the MEC and the EB prime. But this is a co-moving again. This is a synchrotron frequency, but you have to put a gamma because a jet is moving. So this actually gives, enables you to estimate what is a typical frequency of the synchrotron emissions, with, the correspond to the electrons with Lorentz factor of the minimum Lorentz factor. And again, you can derive the scaling relation because this is B is a gamma to the 3 over 8, and this is a gamma to the minus 3 to the 4. And then basically you get minus yes, for the minus 88 or something like that. Oh, sorry, so something wrong. Something wrong. Got it. Sorry. T to the minus 3. Minus 3 over 8, and T to the minus 3 over 4, and then this is T to the minus 3 over 8. And basically you have T to the minus 2. Okay, this is the right stuff. Something like that. So that you can actually calculate how the spectrum, the characteristic frequency evolves. So one more thing. So you can actually, in the very, very high energies, so
then basically you can calculate the synchronous spectrum, right? Then because the electrons spectrum is here, then if you consider the basically the synchronous spectrum is if you consider the one single electron energy of the electrons. So the spectrum of electrons is essentially something like this. F nu is actually the power index is nu to the 1/3, and the tail. And this is essentially order of the 2 pi gamma s square MEC EB. Then if you consider the power law spectrum, something this, then you can actually expect that the total spectrum is a kind of convolution, right? Is it right? So basically you expect that this is kind of the spectrum and this. I think that I can calculate the integration, but I'm not sure how much I have time. Yeah, probably it's better to, yes. I just, I think that you can do the integration, but I skipped this calculation. And then basically, by integrating convoluting the electron spectrum and the synchronous spectrum, basically you can calculate the synchronous spectrum for the power law electron distribution. Okay. Then this is this, right? So I just give the answer. And this is nu to the 1/3. Okay? But one thing physically, the very, very high energy electrons actually should be subjected to the electron cooling, right? Because physically the electrons are accelerated. In here, I just calculate electrons has a power spectrum. Just calculate the spectrum of the synchrotron emission for this electron distribution. However, the very, very high energy electrons spectrum distribution is modified because of synchrotron cooling. So this happens here. This is a cooling Lorentz factor. So that because you can during the dynamical time, basically essentially the comparable to the shock crossing time, and electrons are cooled. Then this is determined by the synchrotron cooling time. When the synchrotron cooling time becomes comparable to the dynamical time. Okay, these are kind of two time scale. This is related to energy loss, and this is related to dynamics. The dynamic time is actually the you already learned. This is actually related to co-moving time scale. So that because you consider it as a system, this is essentially the L prime over C. Okay. Then what is L prime as a function of R? Do you remember? I think I wrote down there somewhere. L prime is R over gamma. Yeah. This is co-moving. R over gamma C. So the R over gamma C. Synchrotron cooling is electron synchrotron cooling is this here. And then 6 pi, and then sigma Tc, the B square, and the gamma E square. And then basically the T synchrotron is by C, and M is C and then R B square and gamma E and sigma T. Does it make sense? Yes. Is okay? This is a synchrotron energy loss, and you can actually calculate the synchrotron cooling time. And then you have the dynamical time, and then you can equate these two expression. Sorry, this is R. And then if you equate these, actually you can get this factor. So the cooling Lorentz factor, this is a characteristic Lorentz factor. Basically, if the energy of electrons, Lorentz factor of the electrons is larger than these factors, basically electrons are cooled during the dynamical time. Basically, spectrum is actually steeper. Steady state spectrum is essentially steeper than the injection spectrum. Yes. It's okay. So basically, using these. This means that you consider the electron distribution is a power law, and you have the gamma minimum, and this is the gamma m. But if the Lorentz factor is consider Lorentz factor, this gamma c prime, this is where cooling is important. Above these energies, so the spectrum is essentially steady spectrum is modified by this because of cooling. Is okay? At least you get the sense. So the basically S, and this is a gamma e to the minus S minus 1. So as a result, of course, spectrum on the synchrotron emission is also modified. Yes. And then in this case, you'd also expect that, I don't know how to make it color, but basically I should modify the spectrum is here. So you have this, and then if you consider this nu m and nu c, and here you get the 2 minus S over 2. Because the spectrum is steeper, then you have the steeper. This is the kind of standard prediction of the synchrotron emissions in this kind of setup. And then basically the people, this is a standard theory. So then here's actually similar to what I had. This is the afterglow spectrum. So as I said, you find that this is characteristic frequencies corresponding to the minimum Lorentz factor. Then below this energy range, this frequency, you have the 1/3. Just 1/3. Then above this frequency, basically this is a nu to 1 over p, and then I use as S, but p is the same as S. And then you have the above the cooling frequency, these energies, you have the nu over p over nu to the p over minus p over 2. Okay. So this is now, of course, here, low frequencies, you need to think about synchrotron and self-absorption. But if you, as long as you consider this energy frequency range, basically you understand what the synchrotron spectrum look like for the given setup. Then this is actually the standard afterglow predictions, and then important things that after the discovery of the GRB, after the discovery of the GRB afterglows, this theory is successful, turned to be quite successful. And then basically the parameters you need is actually the energy of the explosion energy, basically kinetic energy, and then you introduce a phenomenological parameters. How much energy goes to the electrons, how much energy goes to the magnetic field, and the ambient number density, and the spectral index of electrons.
then you can fit the data, then the optical, radio, X-rays. And then people fit it, and then they found that typical parameters they found is that in the case of long gamma ray bursts, the isotopic energy of the order of the 10 to the 53 erg to 10 to the 54 erg, and then okay. Then in the magnetic fields is the order of the typically is 10 to the minus 3 to 10 to the minus 4, and then energy fractions which go to the electrons, the 1% to 10%, and the spectrum index is the order of the 2.2, 2.4, or something like that. And then one more thing, then what happened to the jet? So the blast wave. So the blast wave, actually Lorentz factor is huge initially, but after the acceleration, Lorentz factor decreases, right, as a function of time. Then eventually what happens is that you start to have a break in the afterglow light curve. This is, again, special relativity effect. Because in the early time, because the jet is moving relativistically, right? Then basically emission is also beamed. In the common beam frame of the jet, basically the emission is almost isotropic, right? Isotropic. Then basically boosted. But once the jet is decelerated, and then eventually when the jet Lorentz factor is lower than the inverse of the opening angle, theta, and then actually you start to see the whole jet, okay? Then basically in the beginning, okay, here is the observer, right? Lorentz factor is huge. Basically you see the various, the emission is quite beamed, right? Then jet is expand. Then eventually you can see the the more regions from the jet, right? Because beaming is actually initially it's quite highly beamed, something like this, and then later the beaming factor the beaming is factor is less, right? And sorry. Yeah. And then at some point, when the Lorentz factor is comparable to the inverse of the, comparable to the here, this happens here, basically you see the entire jet, okay? You see the entire jet from the edge to edge. Is okay? Then if the jet is actually quite really spherical, actually you would keep to seeing this kind of power. But it's not true because the flow is collimated. Beyond the edge, you don't have outflows with a similar manner. Okay. Then if for example, if everything is empty, outside the jet, then eventually so emission is actually we don't have a contribution from the jet region outside jet. Then this implies that you start to you start to have a kind of the suppressions. You start to see the suppression compared to the what you expect for the spherical distribution. This is jet break. This is actually regarded as evidence for jet. The fact that we see this kind of break allows us to estimate the opening angle, right? Because this is something the jet break time. And then at that time, because if you calculate the evolutions, you can estimate the Lorentz factor, okay? And then if you know that Lorentz factor is at this time, and then you can actually this jet break, and then you can actually estimate the jet opening angle. You can do that. This is usually the factor of Hugh at the time. And then once you take into account that you can estimate the jet opening angle, right? And then you can actually now estimate the true energy of the jet. Because in the beginning, because everything is beam, what you can estimate is that isotropic equivalent energy. So the energy estimated assuming that everything is spherical. And then this is the E iso. And then this is the true energy. And this is related to beaming angle. So roughly speaking, this is a theta square over the D iso. You consider conical, basically, the double-sided jet. So if you apply this relationship and then just to make a corrections of the jet opening angle, and you can estimate the true energy of the gamma rays or kinetic energy. And then this is here. Then you can estimate the distribution of the jet energy, which is actually the order of 10⁻51 erg. This is actually important in view of the energetics. Because if you consider 10⁻53 to 10⁻54 erg, okay, it's too huge. And then, for example, what is the rest mass energy of the one solar mass? Well, mc square. What is the rest mass energy of the one solar mass? Can you calculate? 54? Yes, 54. But if you see the 10⁻54 erg problem, right? So basically almost 100% energy of the rest mass energy goes to the jet, which is unlikely. So, and 10⁻51 erg is quite comfortable. Then supernova, indeed, you see the kinetic energy of 10⁻51 erg. Okay, so it's not so. It's still we are not sure how you can give the energy to the jet, but 10⁻51 erg is probably okay. It's much more conservative.
But in how many cases do we see the break, and do we see that all frequencies?
This is a very good question. And yes, and then sometimes we see the jet break in the all frequencies, optical X-rays, and but usually the X-rays, some cases the X-rays behave as quite weird. Then sometimes we see the break in some frequencies, and the other ones actually you don't see the clear break. And then I will discuss this issue later because X-ray behavior looks weird, and then we don't fully understand what's going on. But part of the reason is that probably central engine plays a role in the X-rays. Okay, so afterglow theory is very successful. Actually the golden example is a recent event, GW1708-17. So in this case, it's a bit complicated because actually we don't see the jet from the on axis. It's off axis, I explained. And actually here, and initially in this case the story is a bit different because initially you don't see the emission is not so bright. But later, because you are here. So later you start to see the emission from the jet. So if you wait, and use the emission, the afterglow emission is brighter. And then this is what you expect for the off-axis jet. And then anyway, so here just I show the spectrum first. And then it's at least you see that very beautiful synchronous spectrum, just a parallel from the radio to X-rays. And then you can feed the data, and then with the afterglow theory, this spectral index is 2.2, and the density is around 10⁻³ to the 10⁻⁵ to 10⁻⁴ per cubic. And then, as I said, yes, we see the kind of jet here. And then you see basically this is actually when the Lorentz factor becomes comparable to the jet opening angle, to the inverse of jet opening angle here this time. So this is basically around here. Around that time, you start to see the whole jet, okay? And then, sorry, the more exactly I have to consider viewing angle, sorry. You have to, here's the viewing angle. Because here you see the jet, and here this is the observe angle. So basically, you have to wait a bit more. Sorry, gamma is gamma observe 1. Okay. Because if you here in the edge, then you start to see the jet around the Lorentz factor becomes the inverse of theta, but you are a bit off. Then you have to wait a bit more. And then you start to see the whole entire jet. And then one of the important facts is that, in that case, because of data, actually, people think that actually the jet is actually structured. It's a not simple jet with a conical jet. The reason why is probably in the case of the neutron star mergers, actually, in the case of long GRBs, you have a star. But even in the case of neutron star mergers, when the neutron stars merge, and then actually some material ejected because of the tidal interactions, tidal tail, and also the disk wind. And the simulation suggests that the material should be injected when the neutron star merger happen. Then the jet have to go through this kind of ejector. And the same problem happens. Jet have to actually go through and penetrate some material. And of course, when the jet interacts with the ambient material, and you have a kind of the heat, shock heating, and cocoon, and this kind of some material, the hot material, is accompanied, and this affects the structure, entire structure of jet. And this is the reason why we see the kind of the more extended regions in the data. And then one thing on the GRB afterglow emissions, this is something related what the bit more complications. So I talked about this phase. So the afterglow emissions in around 1 day. But Swift was launched in 2004. But they can quickly start observations around probably around 100 seconds or something like that, 20 to 70 seconds. They were able to measure the early afterglows within the hours after the burst. Then it turns out that the behavior of the X-rays in the early afterglows is quite weird. So you never expect that here. But somehow the X-ray emission is sometimes actually shallower than the theoretical prediction. Now, we don't have a complete agreement, so the people discuss the different possibilities to explain this behavior. And maybe energy injection happens, energy injection from the central region happens. Maybe the acceleration efficiency may be different in the early phase because Lorentz factor is much, much larger. And the jet structure affects this kind of the features. And in the radial structure or angular structure might be relevant. And but at least we know that the central engine can be quite active. And then, for example, we see the flares. Even after the prompt emission ends, in the afterglow phase, you see the flares. And then sometimes actually the continue happens in the 1 day later, and this is seen in the X-ray burn. And apparently it's kind of common. At least 1/3 or half of the GRBs have this kind of flares. And even more, the more weird thing that this kind of the extended emissions, long-lasting emission was observed in the short GRBs. So in a sense, the short GRBs are not short. Short GRBs as explained that the duration of the prompt emission is 0.1 to 1 second. But later you have sometimes extended emissions, and this is the duration 100 seconds to 1,000 seconds. So in a sense, short GRBs are not short. And people think that this is actually the related activities of central range. So when the neutron star merger, for the, some neutron star merger or neutron star black hole merger happened, then maybe the black hole accretions, and this powers some late time activities. Or when the magnetar is formed, the magnetar try to keep the energy, keep injecting the energy. This kind of the late time activities might be responsible for the this kind of short duration, long-lasting emission. Okay, so just I want to make a summary for the gamma ray burst, and then I'm switch to some supernova GRB connection. So the GRB is actually the brightest explosion phenomena in the universe. And these emissions come from the electric jet. And we have prompt emissions, astrogrowth. Long GRBs are related to the death of massive stars. And short GRBs are related to the coalescence of neutron stars, likely. And central engines can be black hole, magnetars. We don't know. Then jet composition is actually the big question, magnetic or radiation dominated. And the dispersion emission mechanisms actually, so for the prompt emissions, actually still under debate. And the aftergrowth theory is quite successful, except for the subproblems. And numerical simulations are going on. And to these kind of questions, we need more data, multi-messenger data, and also the high energy observational data. Okay, so just I'll switch to the next topic. So,
are you sure you don't want to stop now?
Oh.
Up to you. I mean, 5 minutes maybe for discussion.
Already, 5 minutes for this.
Up to you.
Okay, 8 minutes, I think. So,
yeah.
Yes.
Up to you.
Okay, I'd like to probably talk about some stuff.
Okay.
Yes. Because it took time to more than expected. Okay, so supernova stuff, and then I said that GRBs are related to supernova. And a supernova is, of course, so 1987 was already observed as a multi-messenger transient, okay? And then these supernova are just already suggested the death of massive stars many, many years ago. So the Baltic is the 90s, early 20s, and they say that supernova process might occur every star once in a lifetime, making first cessation of the existence of ordinary star. And then they also suggest that this is related to the formation of a neutron star. And then, this happens in the very high density regions, very compact regions. And then the reason why I wanted to talk about this is actually we discussed this topic yesterday. So supernova is actually I expect it to happen for the massive stars at the end of the massive stars with a mass of the larger than 8 to 10 solar mass. So basically, initially the star is expected to have such an onion-like structure, and you have an iron core. But the iron cores eventually, I'll explain later. But the iron cores actually collapses, and the gravitational collapses because of gravitational instability, and then eventually the neutron star is formed when the density becomes comparable to the nuclear density. And then still the matter is for the accreting, and this but matter is actually the bounced because of neutron star, and eventually this kind of shock can revive, that you can have a supernova. So basically the energy is comes from the gravitational binding energy. You can estimate the gravitational binding energies, and then just gm square and r by putting the number of neutron stars. You get that this is order of the 3 to the 4 times 10 to the 53 L, right? And then this is actually most of the energy is carried by neutrinos. And the observation of the neutrinos from 1978 actually basically to confirm this. Basically, it's consistent with this kind of binding energy of the gravitation, because the observed energy is order of 3 times 10 to the 53 L. So this is a kind of detailed story. And then if you have a star, and yes, initially the core, iron core, the onion core, then the electron capture or the photodissociations. So either process actually reduces the adiabatic index of the in the equation state. Then becomes the star core becomes gravitationally unstable, and then you have a collapse. And then the neutrinos are trapped around that time, and the density actually increases, and eventually reaches the nuclear density, which is 10 to the 14 to 10 to the 50 gram per cc. And then after that, the equation of states becomes stiff, and you have a neutron star, and then but matter still accretes, and then you have a core bounce, and then basically bounce, and then you start to have a shock. And then after the shock, actually it propagates in the core. Then basically most of the nuclei and then disintegrated, and it becomes neutrons. And then basically you have a neutralization, and associated to the neutrino emission is expected. Then eventually the shock actually leaves. Shock leaves a proton-neutron star, and still keep going, but it's not so easy to keep going, and because the matter is accreting, still accreting. And if you don't have energy injections, basically the shock stops. But people believe that because the proton-neutron is so hot, because neutrinos actually emitted from the neutron, then basically neutron heating happens, and then try to inject the energy, and this may lead to the explosion. This is so-called delayed explosion. Basically, it's accretions, but you have to keep injecting the energies by neutrinos, and then try to overcome this stuff. But this is obviously difficult problems, and at least in the one-dimensional calculations, and for the very massive stars, people fail to have a successful explosion. And then simulations are necessary, and the people are doing the multi-dimensional simulations, taking into account the details of neutron transport and other microphysics. So yes, this is a sample image, and then people actually 3D started to do the 3D dimension. Then basically, okay, so some cases, people start to see the successful explosions, but still the research is actually ongoing. So supernova is actually the multi-messenger source. So that you see the neutrinos, and then in principle, you can have a gravitational wave. But here, actually, still the important things that late time emissions. You also eventually expect electromagnetic emission. When you say the supernova, and you can see the supernova by telescopes. Basically, what you see is actually the late time emissions around, after the few days. Because around just after the collapse, system is so dense, right? You just stir. Then when the shock is propagating inside stir, photons cannot get out. You don't see. Then you have to wait. Then question is that when you start to see the first photons, right? Eventually, you should expect some emergence photons. This is actually the shock to break emissions. So this eventually is, initially the shock is actually propagating inside the star, but the shock is actually keep propagating. The eventual shock reaches the edge of the star, right? Reaches the star. And then after that, of course, outside the stars, density lower. And then basically you start to see the photon. This is the so-called shock breakout. And then because of shock, material is heated by shock. And in this case, this emission is expected in the ultraviolet or X-ray range. And indeed, now recently we started to observe such a kind of shock breakout emission. This is one of the examples. And this is actually the supernova observed in the supernova surveys. And then this galaxy is actually UV satellite, ultraviolet satellite. The people actually investigate the archival data, and they found that there are counterparts in the ultraviolet range. So this is a kind of UV flash. And then this is actually consistent with breakout emissions from the shock. Basically, the shock is propagating when it leaves the star, and then consistent from the shock breakout emissions from the red supergiant. So, okay, so then probably I stop here. So then I have some remaining slides to describe the supernova GRB connections. Then probably I need to discuss probably tomorrow. And then after that, I try to probably discuss some neutrino stuff. Okay, so do you have any questions?
Thank you. Questions? Some urgent ones, because others can wait for the discussion session, I guess. But at least one, otherwise no coffee. I will be generous. 1. Okay. Nobody else? That's the best offer? Okay.
I'm just curious because you mentioned that the power spectrum dependence on the Lorentz factor on the gamma. So you said it's just a model that we use, but is there any reason behind it?
Also power dependence? Sorry. So what?
The and the gamma.
Oh, this is
GRB.
motivated by shock acceleration. Then people just usually expect that particles are accelerated by shock and external shock. And in this case, shock accelerations, typically the Fermi theory that predicts that the spectrum is around 2. Then that leads people just assume the power of spectrum. So, however, in reality, it's not so surprising to have other components. For example, here I just consider the component of the non-thermal electrons, but in reality, just particles, in the case of relative shock, particles can get some energy just by the Lorentz boost. Just Lorentz factor, right? And then thermal population should exist. This kind of populations, in principle, can emit some synchrotron emission.
Any really urgent question? Okay. If not, let's thank Kohta again. We'll reconvene for the discussion session afterwards, okay? Switch off, right? Otherwise the camera is getting crazy.
Oh.